So for electrical circuits, what are the main things you encounter in an electrical circuit? What sort of objects would you clip together to make one?
Resistors, batteries, and wires.
Yeah. So if we look at each of those individually, battery, resistor, and wire. And we've got some standardized ways we draw those in the circuit diagrams. The wire we typically just draw as a straight line. It doesn't have to be straight, it's just easier to draw usually if you just use straight lines and right angles. But the shape of the wire doesn't matter. All that matters is what's connected to what else. And if we're looking at just a segment of wire, we often draw dots on the endpoints. These just sort of imply this is presumably connected to something else. We're just not showing what else it's connected to. As opposed to a resistor. Resistor we usually draw as sort of a zigzag, which of course doesn't necessarily mean the wire is actually shaped like that. It just means we're talking about a section of conductor that makes it difficult for the current to flow. So for instance, a resistor might be a section of wire made out of a material that's more difficult for current to flow through, or a resistor might be some device that is designed to turn the electrical energy into something else. Like a light bulb, for instance, turns the electrical energy into light and heat leaving the system. Or a buzzer turns it into sound and heat leaving the system. As opposed to the battery, usually drawn as a short bar and a long bar. Or sometimes a series of several pairs of short bars and long bars. Traditionally, something like this would represent several batteries chained together in series, but modern batteries are generally several smaller batteries chained together in series anyway, in a unified case. So either of these represents essentially a battery. And what does a battery do? What does a battery provide to the rest of the circuit?
Energy.
It provides energy. And we don't really care so much about the total amount of energy in the circuit, much like in the same way that for fluid flow, we didn't really care about the total energy of the whole fluid. What did we care about? What were we comparing from location to location?
The change, increase or decrease.
And not just the increase or decrease in energy, but energy what?
Density.
Right, energy density. We don't care how much energy the system as a whole has. We just care how concentrated the energy is at each location. And we do the same thing with electrical circuits. We care most about what's the concentration of energy at each point in the wire along the circuit. And the main difference there, for fluid flow, we were defining energy density as energy per unit of volume. Energy over volume. For electrical circuits, we're defining energy as, or energy density as energy not per unit of volume, but what's another property of these electrical circuits that we use instead of volume? How would you describe how much electricity or how much electrical stuff is in one place or is moving?
Voltage.
Voltage is related, but it's not really the stuff that's moving around. In this electrical circuit, what's actually flowing through the wires?
A current, or I think it's like electrons, maybe?
Yeah, the actual particles that are moving are electrons. You've got a series of copper atoms in the wire, or whatever material the wire is made of. One of those atoms maybe has too many electrons. So one of the electrons jumps off and hits the next one, which now has too many electrons. So one of them jumps off and hits the next one. So you've got this chain of electrons in motion. Any one electron doesn't necessarily move very far, but you've got this, all the electrons are in motion in unison. Very much like a bicycle chain drive, for instance. You turn the pedals and you're making all the chain links move at once, even if any one of them doesn't move very far. So the electrons are moving around in the wire, but what's important about electrons? What do the electrons carry that we actually care about?
Charge.
Yeah, and charge is really what we're going to be measuring here. It wouldn't really make sense to measure how much energy like a cubic centimeter of electrons has. Measuring the volume of electrons isn't very useful. So instead, we look at it in terms of energy per unit of charge. Energy density is in electrical circuits means energy per unit of charge. That is E over Q. So E represents energy, capital Q, or sometimes lowercase q represents charge. And we call that voltage. Voltage is an energy density. It's just energy per unit of charge instead of energy per unit of volume. So that's generally going to be written as capital V. So this is what voltage means. Voltage is just the energy density for electricity. It's how much energy each unit of charge has. So in a way, it's very much like the energy density in fluid systems, or even specifically the pressure. So when we talk about the voltage at a location in the wire, that's like talking about the pressure at a location in a pipe. It's the amount of push that makes things flow. And as for units of measurement, what's energy typically measured in?
Joules.
Yeah. And have you seen a unit of measurement for charge yet?
For charge, we did joules per second for power.
Yeah, but that's energy per unit of time.
Charges in like voltage.
Well, voltage and charge are different things. Charge is a property that certain particles have, like electrons, and that's what's moving around the circuit. Voltage is how much push there is on those charges. Amps is a measure of current, which is how fast current is flowing. Charge is generally measured in units called coulombs, generally abbreviated as a capital C. So voltage, that is energy over charge, would be measured in joules per coulomb, J over C. And that is abbreviated as volts. So joules per coulomb is abbreviated as volts. And that's the same volts you see on battery labels. Like if a battery is labeled 9 volts, that means it provides 9 joules of energy to every coulomb of electrons that flow past. And that's really all a battery does. A battery provides a boost in voltage, which is very similar to what fluid flow object.
Pump.
Yeah, a battery is very similar to a pump. A pump provides an increase in pressure. If you've got a pipe with a pump in it, one side of the pump has low pressure, the other side of the pump has high pressure because of the way the pump is pushing on it. So a pump provides a difference between a high pressure zone and a low pressure zone. A battery provides a difference between a high voltage zone and a low voltage zone, voltage being the electrical version of pressure. And typically the battery is labeled with a positive side and a negative side. The positive side is generally the long bar and the negative side is generally the short bar. It'll often be labeled with a plus sign and a minus sign, but if it's not labeled, the shorter bar is meant to be the negative terminal and the longer bar is meant to be the positive terminal. So the negative terminal is going to be associated with a lower voltage. The positive terminal is going to be associated with a higher voltage. So we can say that this battery has a high voltage zone and a low voltage zone. The whole point of the battery is that it's got a chemical reaction going on inside that creates a difference in voltage, high voltage on one side, low voltage on the other side. Much in the same way that a pump pushes on the fluid to create a high pressure zone on one side and a low pressure zone on the other side. Any questions on that so far? And a resistor also involves voltage. But for a resistor doesn't really provide a boost in voltage. Instead, if you've got let's say you've got a low voltage zone on one side of a resistor and a high voltage zone on the other. And presumably these voltages would be caused by something else. Maybe you connect this to a battery and this end is connected to the positive terminal, creating a high voltage zone. And this end is connected to the negative terminal, creating a low voltage zone. If there's a difference in voltage across a resistor, what would you expect to happen? Well, the drop in voltage is just this difference in voltage. The fact that we have a high voltage zone on one side and a low voltage zone on the other side, that is the voltage drop in the sense that there's a difference in voltage. It might help to look at this in terms of fluid flow again. If we go back to, if you imagine a pipe and you have a difference in pressure, let's say you have a high pressure zone on one side and a low pressure zone on the other side. What's that difference in pressure going to do to the pipe? Or if we were to write out a Bernoulli equation comparing these two locations, there's a difference in pressure, so there's delta P. Is there anything else going on in that Bernoulli equation? If we're comparing, for instance, this location and this location.
Resistance?
Yeah, presumably this pipe has resistance. Even if it's not explicitly labeled, any pipe has some resistance. It's just that in many cases, we round that off to 0. But if there's a difference in pressure and there's nothing else going on, no height difference, no area difference, and no pump, the only other term that could even be in the equation to account for that is the negative I times R. In other words, the pressure difference causes what to happen? What happens within this pipe because of the difference in pressure?
Flow towards low pressure?
Yeah.
Yeah.
According to this simplified Bernoulli equation, the difference in pressure causes current to flow through the pipe that has resistance. R, the resistance, is just a property of the pipe itself, whether there's current flowing through it or not. But the fact that there is a pressure difference means current has to flow. And it's going to flow specifically from where to where?
From high to low?
Yeah, that's ultimately what the negative sign signifies here. The negative sign means current is flowing in the direction of decreasing pressure. So we get current, fluid current, flowing through the pipe from the high pressure zone to the low pressure zone. And this proportionality, the fact that delta pressure equals current times a constant, means that the more pressure difference you have, the faster fluid will flow. Or to put it another way, the faster fluid is flowing, the more the pressure decreases. But I think in many cases, it's better to think of it as the difference in pressure causes fluid to flow. Or if you're looking at just some small section, you could say the fact that fluid is flowing means there is a pressure drop from location to location. And in electrical circuits, resistors behave in almost exactly the same way. Different values for the, or different meanings for the variables, but still the same structure. Instead of pressure, we're talking about voltage. The fact that there's a difference in voltage means electrical current will flow through this resistor, again, from the high side to the low side, from the high voltage side to the low voltage side. So we're going to get electrical flow, which we're still going to call current, or capital I for current. So we still have current flowing. It's just that current means something different here. If we go back to fluid flow, how did we define current for fluid flow? What did we mean by current?
Amount of volume per second.
Yeah, volume per second. It also happens to equal area times speed because of the geometry involved. But that's not what current means. For fluids, current is defined by volume over time. So current means how much volume of fluid flows past a point per second, the volume over time. Like if we say that the current is 5 cubic meters per second, that means every second, 5 cubic meters of fluid flow past that point in the pipe. But if we take a look at the electrical version of that, we don't want to talk about the volume of electrons because that would be ridiculous to measure. What's the important property of electrons we care about instead?
Charge.
Yeah. So current means not volume over time, but charge over time, specifically change in charge over change in time. That is how much charge flows past that point on the wire per unit of time. Again, charge is still measured in coulombs. So the units of measurement here are going to be coulombs. And then time as usual is measured in seconds. And we abbreviate that as amperes. Amperes, or sometimes just amps. So 1 amp or 1 ampere means 1 coulomb of charge flows past that point on the wire every second. And amperes is abbreviated as capital A. So 1 ampere is 1 coulomb per second. Or written as an equation for the definition, I equals delta Q over delta T. Current equals change in charge over change in time. So this is what current means for electrical circuits. Current means how much charge flows past that point per second, how many coulombs per second, that is how many amps. So when we say the current is 5 amps, that means 5 coulombs worth of electrons flow past that point every second. Any questions on that so far? And we can bring an equation into this also, much in the same way that for fluids, the pressure difference is proportional to the current. For electrical resistors, we can also say, instead of pressure, the voltage difference is proportional to the current. So we'd say delta voltage is proportional to the current. In other words, delta voltage equals something times current. So for instance, if you want twice as much current, you're going to need twice as much voltage to make that happen, or twice as much voltage difference. Much like with pressure, we generally don't care what the voltage is, we just care what the difference is from location to location. So that constant of proportionality, we're still going to call R. So we're still going to have current times resistance. We're still going to have a negative sign signifying that the current's flowing in the direction of decreasing voltage. So the structure is almost the same. Right? I should really say the structure is exactly the same. Delta V equals negative IR. That's essentially the same structure as this simplified Bernoulli equation for a pipe with resistance. The only difference is what the variables mean. Instead of current as volume per second, we're looking at electrical current as charge per second. Instead of pressure as a fluid energy density, we're looking at voltage as an electrical energy density. And instead of the fluid resistance of the pipe, we're looking at the electrical resistance of that section of whatever this material is. And as for units there, voltage is still measured in volts. Current is measured in amps. And resistance is measured in a new quantity called ohms, written as the Greek letter capital omega. So ohms is the unit of resistance for electricity. And what would ohms equal in terms of the other units? If you actually solve this for omega, what would you get? How would you isolate omega in this equation?
It'd be volts over amps.
Yeah, volts over amps. So volts is the electrical version of pressure, the electrical push that causes current to flow. Current is measured in amps. That's describing how fast charge is flowing through this wire in terms of charge per second, coulombs per second. And then ohms is a measure of difficulty. More resistance measured in ohms means it takes more volts to get the same amount of current. So the amount of push required equals the flow rate you want times how difficult it is to flow through that resistor. In much the same way that the pressure difference that it takes to make fluid flow at a certain rate equals the current rate you want, the fluid flow rate you want, times the resistance of the pipe. Same structure, just different meanings for the variables and different units of measurement. Any other questions on resistors so far? And that equation, the formula for delta V for a resistor is usually called Ohm's law, the same ohm that the unit of measurement was named after. So any resistor is going to provide a difference in voltage proportional to the current. That is, the faster the current's flowing through the resistor, the more the voltage difference will be. We usually call that a voltage drop because it's a decreasing voltage in the direction of current. Or to put it another way, the more voltage drop there is, the faster current will flow. But this equation is ultimately the core idea of a resistor. A resistor is a thing such that the more voltage there is, the more current will flow through it, directly proportional. Whereas the battery provides also a voltage difference, but that voltage difference doesn't care how much current there is. Much like a pump provides a constant boost in pressure, the battery provides a constant boost in voltage. So we would typically write that as delta V equals plus some constant, usually written as epsilon. This is just saying the battery provides a constant boost in voltage. That boost in voltage is sometimes called the electromotive force, or EMF. Though it's not really a force, it's much more like a pressure, but it's called the electromotive force in the sense that it's what's pushing on the current, what's pushing on the charges. So we've got voltage difference for a battery. We got voltage difference for a resistor. What about wire? If you're comparing any 2 points on the wire, what would you expect about the voltage? With this wire, sorry, go ahead.
Oh, I was about to say that they should be the same.
Yeah, if we've got no battery, there's no boost in voltage. If there's no resistor, there's no drop in voltage due to current flow. If you're just talking about wire, the voltage is the same everywhere. So I think this is really probably the most important thing about wire. If you've got any 2 points connected by just wire, there's no difference in voltage. So wire can be thought of as a convenient way to transfer voltage. If you have 2 points that you want to be at the same voltage always, connect them with wire, then they're guaranteed to be at the same voltage. This is assuming the wire has zero resistance. Realistically, any wire does have a little bit of resistance. It's just that that's usually small enough to round off to zero. The only exception would be if you have a colossally huge amount of current flowing through it, in which case the tiny resistance does matter. But a wire, we generally assume the resistance rounds off to zero, and therefore there's no delta V. Any questions on that so far? A little later, we're also going to look at an idea called a capacitor, which is basically two metal plates, not connected to each other, but close together and joined with or connected to wires leading elsewhere. So if you want a complete list of all the circuit elements we're going to need, this is a capacitor and its voltage difference formula associated with it is negative charge over capacitance, Q being charge and capital C being a measure of the capacitance. That is essentially the efficiency of the capacitor. So we're not going to need that for a while, but you might want to write it down in your notes just for future reference if you want a complete list of all the delta voltage formulas you'll need. Any other questions on voltage or any of the new terminology so far?
Sorry, but for the new equation of the capacitor that you introduced us to, is C coulombs again?
C here is capacitance.
Okay, thank you.
Capital C as a unit of measurement is coulombs. Capital C as a variable is capacitance.
Thank you.
Which can be thought of as the efficiency of the capacitor. In the sense of how a capacitor essentially is a device to store charge. You can get charge, like positive charge building up on one plate and negative charge building up on the other plate. The capacitance describes how well it can store charge. And the more charge is built up on it, the more voltage it will provide. Again, we're going to get to that later. In terms of analogy for fluid flow, you can kind of think of a capacitor as being like a water tower. You can pump more and more and more water into it, but the more water you pump into it, the harder the water pushes back against the push. Whereas a resistor acts like a pipe with resistance, a wire acts like a pipe with a negligible amount of resistance, and a battery acts kind of like a pump. Any other questions on this so far? Then let's try out some examples. Let's say, I'm gonna clear this for now. And let's say we have an actual circuit. If we actually join some of these together, let's say we've got a battery, and let's say it's connected to a couple of light bulbs. Light bulbs are usually drawn like this, like a wire with a little lump in it or a loop, and then encased in a glass container. Formally, this is supposed to represent the filament of the light bulb and the glass bulb around it. But this is just the symbol for a, so this would be two light bulbs. And what does a light bulb actually count as in terms of what we've seen already?
A resistor?
Oh, yes.
A light bulb is just one example of a resistor. So light bulbs count as resistors, buzzers count as resistors. I'm pretty sure motors count as resistors, though the magnetic effects going on in that might make it a little different. But essentially anything that uses the electrical energy to do something else or convert it to another form of energy transfer is going to count as a resistor. And let's say we know some of the information here. Let's say we know that the epsilon of this battery is 12 volts. Let's say this is a 12-volt battery. And let's say we also know the resistances of both of these light bulbs. Let's call those, let's say R1 is 4 ohms and R2 is 2 ohms. So one of the light bulbs has twice as much resistance as the other. And this is usually information that's provided. In an actual real world situation, a resistor is typically labeled with what its resistance is in ohms, and a battery is typically labeled with its voltage. So in a case like that, if you know all of those values and you connect them together with a wire like this, what else do you think we'd be able to solve for here?
Current, using the loop rule.
Yeah. And since there's only one path, it's just a single loop, what does that tell you about the current in this?
Current should be the same.
Yeah, much in the same way that for fluid flow, if you just have one single path of pipe, then the current is the same everywhere in that pipe because there's nowhere else for it to go. Same thing here. If you just have one path, then the current is the same everywhere along that path. You can get an exception to this if the path splits. Like if you have a junction. But even in that case, the junction rule or the continuity principle still applies. If we have currents like this, what would you expect to be true about these three currents? Let's say we call these I0, I1, and I2.
I0 equals I1 plus I2.
Yeah. The junction rule is that idea that the current in I0 has to equal the current out I1 plus I2. So for any single point, and this is usually applied to junctions because it's called, which is why it's called the junction rule, we can say that the total current going into that point, the sum of all the currents flowing in, has to match the sum of all the currents flowing out. This is called the junction rule, or sometimes called Kirchhoff's current law, in the sense that it is a statement about current. But this even applies to points or regions that aren't junctions. Like if we just look at this corner, we can say the current flowing in must match the current flowing out, which explains why the current is the same everywhere in this loop. There's nowhere else for it to branch off to. So there's only one current we would need to solve for here. I equals, and we don't know what it is yet. And you mentioned the loop rule. What does the loop rule claim?
The total change in voltage is 0.
Yeah, if you're looking at any complete loop, if you start and end at the same point, the sum of all of those delta voltages you pass through must be 0. And this is the same idea we saw with the Bernoulli equation in fluid circuits. If you've got some network of pipes that loops back on itself, if you start at some location and go through a bunch of stuff and get back to the same location, all of the deltas turn into 0. Delta pressure, delta kinetic energy density, delta potential energy density, those are all 0 because you return to the starting point. Same idea here. If you start at any point on the circuit, and you can start anywhere, I usually find it easiest to understand what's going on if I start right before the battery. So starting here, if we travel around the circuit, we have returned to the starting point. So delta voltage overall would be voltage at this starting point minus voltage at the ending point. Those are the same voltage because it's the same location. So the delta voltages of anything we pass through on that path have to add up to 0. And this is also called Kirchhoff's voltage law because it's a corresponding law about voltages. So in this case, as we travel along this path, what do we pass through?
Two resistors and a
Yeah, we're
battery.
passing through 2 resistors and also the battery. So the loop rule would be all 3 of those voltage differences, delta V for the battery, plus delta V for resistor 1, plus delta V for resistor 2, because we pass through all 3 of those things on this path. Those have to add up to 0. And then we can fill in the formulas for each of those delta Vs. Battery, for instance, we saw earlier was always going to be plus epsilon. And we know that epsilon here is 12 volts, but I would recommend writing it out in terms of variables first. And what about delta V for a resistor? How would we write that?
Negative IR.
Right, negative IR. And I would write this, for instance, for 1 as I1 times R1. And likewise for resistor 2, negative I2 times R2. Except what do we know about both of those currents?
They're the same.
Right, the current through resistor 1 and the current through resistor 2 are the same current. So we don't really even need to label these separately as I1 and I2. We could just call them both I. So there's our loop rule equation, plus epsilon, which is 12 volts from the battery, plus negative I, which we don't know, times R1, which is 4 ohms, plus negative I times R2, which is 2 ohms, adds up to 0. And before plugging in the numbers, let's do a bit of algebra. What can we do here since we know that I is the same in both of these terms?
Factor it out.
Yeah, if we factor that out, we get plus epsilon. In fact, we could factor out the negative I and get minus I times, and what's left if we factor out negative I?
R1 plus R2.
Right. And then we could solve that for current. Before we do, though, one thing I'd like to point out, this term now looks like still negative IR. It's just that what has happened to R?
It's split up.
Right. Or I wouldn't really say split up so much as combined, because they were separate resistors, but we put them together. And how would you describe, yeah, these are in series, right? We put these resistors together in series, which forces them to have the same current. Same current means we can factor that out. So all that's left is the resistances added together. 2 or more, could be any number of resistors in series, act like one big resistor with the resistances just added up. And the reason that works in the first place is because they have to have the same current, and so you can factor that out. In general, anytime you got resistors in series, that is, there's just one path that goes through all of them, and there's no other branches you could take that avoids one of them. That means they all have to have the same current, which means you can treat them as just one big resistor with the resistance factored, or the resistances added together. So any resistors in series. the total resistance, or sometimes called the equivalent resistance or effective resistance, is just all the resistances added together. R1 plus R2 plus R3 plus and so on up to R sub n, where you have n resistors. In this case, just 2. Any questions on resistors in series so far? And then if we actually solve this for I, what would you get if you isolate I in this equation? Just in terms of the variables, no numbers yet.
E over R1 plus R.
Yeah, that electromotive force of the battery divided by R1 plus R2. In other words, the voltage of the battery divided by the total resistance. And I think this stands up to what we should expect. A stronger battery is going to mean more current. More difficult resistors, either one or both being more difficult, is going to lead to less current. And at this point, we can plug in the values. 12 volts divided by 2 ohms plus 4 ohms. That's 12 volts over 6 ohms. So that's 12 over 6, 2. And what's volts divided by ohms going to equal?
Amps.
Yeah, that should be amps or amperes. So 2 amps would be the current in this circuit. And that's the whole circuit. There's only one path that current can take here. So all points along that path have the same current, just 2 amps. Any questions on that so far? Also, now that we've got the current, we can find the individual voltage drop across each resistor on its own. Because for any resistor, delta V equals negative I times R. So if we calculate negative I times R individually for each resistor, for instance, for resistor 1, what's the current?
2 amps.
So we can multiply that by the resistance. Resistance times current, 4 ohms times 2 amps. And also with the negative sign, so that'll be negative 8 volts. In other words, the difference from one end of this light bulb to the other end is a difference of 8 volts. And what about for resistor 2? If you multiply negative current times resistance, what do you get?
Negative 4 volts.
Yeah, negative 4 volts. So the 2 resistors together, since they're in series, we can add up the voltage drops. You go through one of the light bulbs, you lose 8 volts. Then from that, as a new starting point, you go through the other resistor, you lose 4 volts. So how much voltage have you lost altogether?
$12 volts.
Right,
The
which
opposite
matches
of
the,
battery.
yeah, the battery provides 12 volts. The 2 resistors together use up 12 volts. So the voltage matches. In fact, you could even, I usually think of this as mapping out the voltages everywhere in the circuit. Let me tighten this up a little bit. If we think of the voltage, and the voltage doesn't really have a baseline 0. There's not really a location we have to call a certain value. I usually find it useful to call the point right before the battery 0 volts, just because that's typically going to be the lowest voltage in the whole circuit. But that's just a reference point. The important thing is the change. But if we say the point right before the battery is 0 volts, let's just label this 0. Also, what other points have to be 0 volts? What else has to be the same voltage as that? How much does the voltage change if we move along a wire?
It doesn't.
So that means all the locations that are connected to this by wire, those are all at the same voltage. This entire region is a 0 volt region. But if we pass through the battery, what happens to the voltage?
It increases by 12.
Right. So that means the point on the other side of the battery is going to be a 12 volt zone. And in fact, not just this location, but all points connected by just wire. This entire region is a 12 volt zone. So we've got a 0 volt zone on the left side, a 12 volt zone on the right side. And also, if we take a look, if we sort of zoom in between the light bulbs, there's going to be an intermediate zone, because if you pass through one of the light bulbs, how much has the voltage changed?
By
What's the, sorry, what was that?
8 volts for the first one.
Yeah, that first light bulb we pass through, we lose 8 volts. So that means the voltage on the other side of the light bulb, in between the light bulbs, that's going to be 12 minus 8, so that'll be a 4-volt region. Yeah, exactly. So this in-between zone is a 4-volt region. Then we pass through the other light bulb, losing 4 volts. 4 volts minus 4 volts brings us back to 0 volts. So by mapping out the voltages like this, we now know the voltage everywhere in the circuit. And if you took a voltmeter or a multimeter and use it to measure the voltage differences, like let's say you hook up a voltmeter one end to this side and the other end to this wire, you're going to measure a difference of 8 volts. Because you can't really measure voltage. You can measure differences in voltage. That's what a voltmeter or a multimeter is all about, measuring the difference in voltage. It's something like you've got 2 prongs, you can touch those prongs to 2 locations on a circuit, and the device will tell you what's the difference between those 2 voltages. So there's not really any way to measure voltage, but you can measure differences in voltage. And that's all we really care about anyway. So I would recommend setting it up in this sort of way. When you're analyzing any circuit, see if you can figure out what the current is through each path, and also map out what's the voltage in each region, each zone. And drawing it out, like highlighting regions of the wire, it's not really an official formal notation. It's just what I find useful for visualizing where the voltages are. At any point, again, any points connected by just wire must be at the same voltage. So if you know a voltage at one single location, you can sort of imagine that voltage spreading out as the same value along wires until you hit something else. As soon as you hit another resistor or light bulb, resistor or battery or capacitor, when we get to that, the voltage could be different on the other side of that thing. But any points connected by just wire, the voltage must be the same everywhere along that wire. Whereas with current, as current flows, if you hit a junction, the current's going to split. Not necessarily evenly, but you can figure out which one gets more or less current based on resistances and filling out the loop rule equations. Any other questions on that so far? All right. Then try out some more examples on your own. If you want some more practice problems to work through, go to math.andcheese.org/P7C. Let me put that in the chat. math.andcheese.org/P7C. The main links you want to look for there are Intro to Electrical Circuits. It's got pretty much all this information about voltages and batteries, resistors, wires, loop rule, junction rule, all the important information organized in one place. And also there's another link to a circuits practice worksheet. It doesn't have any instructions, it's just a bunch of circuit diagrams. But the idea is on each one of those, I give you the voltages of the batteries and the resistance of the resistors, and your goal is to find the current everywhere in the circuit. So try that out. Sorry, go ahead.
I just said thank you.
Oh, yeah, you're welcome. Try that out. Let me know if you have any other questions, and I will see you next time.